Welcome back. So far in this course, we've dominated samples using brute force. We've smashed tissues, breached membranes, and crashed proteins. We've used liters of organic solvent and spent countless hours waiting for evaporation. But today, we are going to do something that feels like laboratory magic. We are going to capture the chemical fingerprint of a sample without using a single drop of solvent. Welcome to the world of SPME, solid phase microextraction. This isn't just a new tool, it's a shift in how we think about sampling. We are moving from total destruction to a sophisticated representative sip of the truth. Have you ever tried to capture the scent of a fresh cup of coffee or a blooming jasmine flower using traditional solvent extraction? Think about the process. By the time you've finished the reflux, the distillation, and the final evaporation, that delicate truth is gone. All you smell in your vial is hexane or methanol. In mass spec, we call this the solvent mask. It creates a massive signal at the start of your run that hides the very volatiles you care about. SPME is the invisible sip. It allows us to taste the air above a sample and send that pure essence straight into the machine. It is chemistry at its most elegant and least intrusive. To master SPME, you have to look past the needle. An operator sees a simple device, a specialist sees a concentrating sensor. Our roadmap for this unit follows 4 strategic acts. First, we examine the magic wand, the fiber itself. Second, we differentiate between the 2 physical traps, absorption and adsorption. Third, we decide where to sip. Do we hover in the air, headspace, or dive into the deep, direct immersion? Finally, we look at the thermal release into the GC per megasiemens. This entire process integrates sampling, extraction, and concentration into one single, solvent-free step. Look at the diagram of the fiber. Inside that protective needle is a tiny fused silica fiber coated with a polymer sponge. When we extend that fiber, we aren't just dipping it. We are exposing a selective landing pad for molecules. As the molecules hit the coating, they are trapped and concentrated. This is the ultimate efficiency. In traditional prep, concentration is a separate, risky step involving heat and nitrogen gas. In SPME, concentration happens automatically as you sample. It's an elegant, passive process that respects the integrity of your chemical fingerprints. Here is the first specialist distinction: absorption versus adsorption. If your fiber coating is a liquid-like polymer like PDMS, the molecules dissolve into the coating. Think of a sponge soaking up water. This is absorption. But if you use particle coatings like carboxin or DVB, the molecules stick to the surface in pores. This is adsorption. Why does this matter? Because porous solids can trap small, highly volatile molecules much tighter than liquids can. A specialist chooses the physics of the trap before they ever pull the plunger. If you pick the wrong physics, your ghost will simply fly away before it reaches the detector. We have 2 modes of operation, and your choice determines the ROI of your sample prep time. First, headspace, HS. This is where we sip the breath of the sample. This is the specialist choice for volatiles in dirty matrices, like soil, blood, or wastewater. Because the fiber never touches the actual liquid, it stays clean and protected from non-volatile gunk. But what if your analytes are semi-volatiles that don't like to jump into the air? Then we use direct immersion, DI. We plunge the fiber directly into the liquid. It is more sensitive for heavier molecules, but it's high risk. The secret to a long fiber life is knowing when to stay in the air and when to dive into the deep. In SPME, one fiber does not fit all. An operator grabs whatever fiber is already on the autosampler. A specialist chooses the coating, like a sommelier chooses a glass for a specific vintage. Are you looking for non-polar fats or gasoline components? You need the grease bouncer, PDMS. Are you looking for polar phenols or alcohols in a beverage? You need polyacrylate. For the most complex missions, like food aroma profiling, where you have hundreds of different molecules, we use the Swiss Army knife, the DVB CARF PDMS triple-phase fiber. It has layered chemistry designed to catch big, small, and polar molecules all at once. If you need even more power, you move from the magic wand to the SPME arrow. Look at the number on your screen, 10x. By increasing the surface area and using a rugged metal core, the arrow can capture 10 times more analyte than a standard fiber. This is the industrial strength version of our technique. It solves the fragility problem of the traditional quartz fiber and allows for much lower detection limits. In high-throughput environmental labs, where we are looking for part per trillion pollutants in water, the SPME arrow is the weapon of choice. It's how you turn a whisper of a signal into a definitive, audit-proof peak. This slide represents the hardest concept for beginners to grasp. SPME is an equilibrium technique, not an exhaustive one. In traditional extraction, you try to take everything from the sample. In SPME, we don't do that. We just wait for the molecules to reach a quote-quote balanced state between the sample and the fiber. Look at this curve. Extraction increases rapidly at first, then flattens out. A technician thinks they need to wait 2 hours for total extraction to get a result. A specialist knows that as long as they are consistent, same timing, temperature, and agitation, they can stop at 15 minutes and get perfectly reproducible data. Consistency is the anchor of the invisible SIP. Remember our salting out lesson from Module 2 to 4? We can use that same strategic weapon here to boost our SPME efficiency. By adding high concentrations of salt to your liquid sample, you make the water extremely You are essentially using the chemistry of the liquid to drive the physics of the air. The salt ions steal the hydration molecules, kicking the volatiles out of the water and into the headspace where our fiber is waiting. This is how a specialist cheats the equilibrium curve to get more signal in less time. We are using every chemical lever at our disposal to make that invisible SIP as rich as possible. Let's put your specialist mindset to the test. Imagine you are working for a premium coffee brand, and a batch has an off smell. You need to find the chemical fingerprint of that odor. How do you design the SIP? An operator might just grab a general-purpose fiber and stick it in the beans. But you decide. Is it a volatile odor? Use headspace to keep the fiber clean. Is the odor musty? Likely polar? Choose a polyacrylate or triple-phase coating. And finally, how will you ensure your results are reproducible? You'll set a precise equilibrium time and temperature. Take a moment. How would your approach change if you were looking for pesticide residues instead? We have successfully completed our briefing on the invisible SIP. We've learned that SPME is the ultimate green technique, saving solvents, saving time, and preserving the delicate truth of our samples. We've mastered the anatomy of the fiber, the decision between air and liquid, and the sommelier's wardrobe of coatings. But if you carry only one thought back to your lab bench, let it be this specialist mantra. In SPME, less is more. We don't need the whole sample to tell the story. We just need a perfectly executed representative SIP. You are now a master of chemical sensing in the gas phase. You've mastered the elegant gas phase SIP. It's perfect for volatiles and aromas. But let's be practical. For bulk, clinical, or environmental analysis, we often cannot avoid the liquid phase. Sometimes we need to process liters of sample for extraction. That is why our next step is to master the bulk phases. Join me in our next unit, Module 2 to 7, Phase Mastery. We are going to compare liquid-liquid extraction LLE with supported liquid extraction SLE. We'll see how modern automation takes these classic techniques and standardizes them for high-throughput cleanup. We've learned how to catch a ghost. Now let's learn how to move an ocean. I'll see you in the next module.